Hi and hello everyone. In this lecture, what we will look at is an overview of stochastic processes or random processes, as you might know already. Queuing theory is a part of theory of applied stochastic processes, because this is the theory that is developed in stochastic processes to analyze the system or can create queuing models, and so that it can be real systems can be analyzed. So, it is basically a theory of part of the applied stochastic processes. Okay. So, what is a stochastic process then, right? So, you have we said that if you have the knowledge of stochastic process, in particular Markov chain, discrete and continuous, you will find the next few lectures will be the things that you already know. If not, you do not need to worry too much on that, because we are going to review in some. This is not going to be a complete detailed study on the required material, but we will just review what is relevant, what are the basic ideas and how things come up, and how we will simply use it in our queuing analysis. So, we are not concerned about the theorem proof approach of this particular theory of stochastic process, but rather we will be using the results and what is the background to the results, what is the basis for these results, and how the proper applicability of this result can be ensured, and that would be our objective. Okay. Because we need to understand on what basis of assumptions, right, this particular result is derived. Just knowing the result is not sufficient, because then you will make mistakes when you are trying to apply to the systems. So, that is the thing that we want to keep it. So, we will just brush up and we will just review in this whole series of stochastic process lectures for the next 2 weeks. But to start with, we will give a broad overview of stochastic processes. So, you will know like where exactly what are the typical type of stochastic process that you use, and what are the other processes that might come handy if you are going little bit higher in the analysis of such even our queuing systems. Okay. So, we will start with what is a stochastic process, right. So, as you know already, if not you can see that a stochastic process or a random process is a family or a collection of random variables, which we denote it by in this manner, where T is some index set and all these are random variables. They are all defined on some common probability space, is what you call simply as a stochastic process. So, any collection, a family, if you take a sequence of random variables, that could also be considered as a stochastic process, right. When the index set is some interval on the real line, right, we will all be worried about the real line and T being this capital T being subset of whether this is a finite set or it is a countable set, or it is some intervals, and the whole of the non-negative interval, non-negative real numbers is what we might have for this particular T, and this is the index. So, we are just denoting in the family, we are denoting the random variable by certain index, and that is what is the index set, which is what we will also call as a parameter, and this T, capital T, is what we call it as the parameter space. Right. So, that is the terminology that we will use. The parameter space means the index where it takes values. Okay. And all these random variables takes particular values, right. So, for example, x1, x2, x3, if you have in a discrete manner, or any x 0.5, x 2.7 and so on, any random variable if you take, they all take value in some particular set. So, if you put together all like the possible values that a particular random variable in this family, not just one, in this family it takes, and then that is what is called, that is a common support for all the random variables in the stochastic process. That is what we call it as the state space, and the notation that we will be using is S. T is the parameter space, S is X. and already you know x is a random variable, meaning it itself already is a function from omega to r, right. This particular omega to r is what each of these random variables are, and on top of it we are putting one more index. So, basically this is a mapping from this t cross omega to r, and hence is a function of both omega and t, right. So, essentially though we write it x of t, but x is a random variable. So, it is already a function of omega. So, it is a mapping, measurable mapping, that is what you know we know already. Okay. Now, in this particular case, suppose if you fix a omega, right, if you fix an omega, then you can look at this as a function of t defined on t, right. It is a function as a function of this argument small t alone, the index alone you can think, because you are fixing a omega, right. And such a function is what is called sample path or realization of a stochastic process. Okay. So, you can view the stochastic process, which is nothing but this family of random variables, as if it is a family of these kind of functions, one for each of these omega you have, and then you put this collection together, and that is what you call it the stochastic process. So, basically a sample path here is a collection of time ordered data describing what has happened to a dynamic process in one particular instance. That one particular instance is what is a fixed omega would mean. So, this is a stochastic process is then a probability model describing the collection of time ordered random variables that represent the possible sample. So, if you put all possible sample paths together, one for each omega, then that is what you are going to get this whole collection is what then would be represented by a stochastic process. On the other hand, if you fix an index, in this index set which is t, then as we said this is just a single random variable. Okay. This is just a single random variable. So, that is a normal view, that is also that is what you know we have set in the beginning, that it is a collection of random variables, one for each t, right. So, it's a random variable. So, in many stochastic processes, this capital T, this often represents time. In our particular case of queuing the models, this will be more of time, but this is a generic word time. It could be, need not be even time, it could be in any sense, even it could be area that could be represented by, right. Suppose if you have a cloth and you are looking for the defects, so the area, the number of defects in a particular area could also represent, this stochastic process can represent. In that case, this t represents the area, but in our case it is simply the time, and we refer x of t as the state of the process at time t. So, remember this word, the state, because you know of the process, when we mean state of the process at time t means we are representing this x of t. Many a time, for again notational convenience, instead of writing this as x within bracket t, we will write it x suffix t. So, but you should understand that this is a function of t, that is how you have to understand. Okay. Now, let us look at some few simple examples of such a process that you could get. As usual, in any probabilistic experiment, you always talk about coin tosses. So, this is one such situation, right. So, you have a coin and you are tossing repeatedly the coin, okay, and you are trying to count the number of heads. So, when you start, the number of heads is 0. So, the process, suppose if I call it as x of t, x at 0 is 0. Then when the first toss comes, one toss is made, either there could be 1 head or 0 head. Accordingly, suppose if it is a fair coin that you had assumed, the probability of these two would be each be half, right. So, that is number of heads, could be either 0 or 1. So, the randomness start creeping in. Now, when you go to 2 heads, you could have the possibilities of number of heads could be 0, 1 or 2 with corresponding probabilities and so on. So, when we go to n number of tosses, then what you are getting is, right, the number of heads would be anything anywhere between 0 and n is what then you would see, right. So, this is a a random process in this case. If you are looking at the number of heads in the first n tosses in a sequence of coin tosses, right. Number of people affected by COVID. So, here the first example, like the index set is basically 0, 1, 2, 3 and so on. The state space is also 0, 1, 2, 3 and so on, right. So, this is what in both cases it is non-negative integers. So, that is what is the parameter space and the state space for this particular example. Like that the other examples also you can make it up. For example, number of people affected by COVID in India as a function of time. Now, like this could be like if you assume the time to be continuous at every instant, you are counting the number of people affected by COVID in India, right. So, then that is essentially the number would be a discrete quantity, right, but the time is continuous. The parameter space is in some interval in this particular case, or daily closing prices of a particular stock in National Stock Exchange, right. Temperature at Guwahati as a function of time is what these are all some simple examples that you can easily think about it. Okay. Now, recall we know completely about a random variable if you know the probability distribution of the random variable, because any question that you have with respect to the random variable can be answered if you know its distribution, whether it is certain probabilities or some expectations or anything of that nature, like it can be answered. In a similar way, but at least the distributional properties, not of the sample path properties, because that is something which you will not be able to do completely, but at least there, as far as the distributional properties of a stochastic process is concerned, they all can be answered, or you can have the complete properties of them if you know what is called as finite dimensional distributions. Just like for a random variable you want to know the distribution, in this particular case for a stochastic process you want to know what are these FDDs. So, what are these FDDs? These are defined in this manner. So, for each n and for each n time points in the index set, if you look at their joint distribution, that is this quantity. If you know, right, if you know this particular probability, which is nothing but the joint probability distribution, the n dimensional joint distribution of these random variables x at t1, x at t2 and so on x at tn, where this n is arbitrary, t1, t2, t3 is arbitrary, and also the state x1, x2, xn is also arbitrary. So, if you can compute these probabilities for all such, so you can compute this completely, that means then you know completely about the stochastic process, but at least their distributional properties, right. So, the question is it possible to get this for all kind of stochastic processes? The answer obviously would be no, because there will be like very complex situations where you will not know completely the joint distributions. You may know few joint distributions, but you may not know completely all joint distributions. But for many interesting stochastic processes, it is possible to provide the above specification in simple terms, right. Now, let us look at how we can group, like this is stochastic process, we define it in a much generic way. Now, how we can classify them or group them into different, so that the particular group which is having a particular properties can be studied in detail, right. That is the normal approach to take when you have this kind of generic quantities that you are looking at it. So, this can be classified or grouped or distinguished based on say parameter space T, state space S, the dependence relationship among the family of random variables, because you know that when you have more than one random variable, you always have a possibility of whether they are related in some sense or they are independent, dependency and independent. So, depending upon the nature of relationship among the family, one can also classify them. Okay. These are the generic way of classifying. As far as the parameter space is concerned, which is the index set, if this set T is a countable set representing specific time points, then the stochastic process is said to be a discrete time stochastic process. Say for example, in this particular case, this T could be of this nature, and in such cases this x of t, we very often we will write it as x suffix n for n greater than or equal to 0 when it is indexed by non-negative integers. So, in case of discrete, it is common that instead of using this t within bracket, it is a suffix n, like in the coin toss experiment that we have noticed xn, x2, x3, x4 and so on, right. So, it is often denoted in this manner. So, if this is the case, then it is always assumed that you have the index which is discrete when you are using the index n. Now, if t is an interval of the real line, then it is called continuous time stochastic process. For example, this t could be the whole of non-negative real line, or it could be even the whole of r in some cases, and so on. So, in this case, like this could be written in this way, or many a time for simplicity, because just we want to avoid this looking little complex, but nothing really complex here. So, it is basically like x suffix t also you can make here. Okay. This is based on the parameter space. You are dividing into discrete time and continuous time, and depending upon the state space, again if the state space is a countable set, right, then we call this as a discrete state stochastic process, and whenever this is of this nature, right, and we call this as chain rather than a process, we normally tend to refer to this kind of thing when the state space is discrete. We refer to the stochastic process as stochastic chain. The chain is the word that is used in such scenarios. Okay. If S is the interval of the real line, then it is called continuous state stochastic process, but in this case S could be even this, or non-negative real numbers, or whatever is the number. Okay. Now, if it is S is an Euclidean n space, then it is an n vector stochastic process. So, depending upon these two, right. So, one can have a discrete time, discrete state stochastic process, and the combinations, the various 4 combinations also you could have. That is one classification, that is okay. But for example, if you look at here the number of heads in the first n task, these same examples that we have seen earlier. In the first case both are discrete, in the second case the state space is discrete, but the parameter space is continuous when you are looking at as a time. Daily closing prices of a stock on NSE, right. So, this the price could be anything, like it is continuous, any non-negative quantity, but daily, that means time you are discretizing is day. Temperature as a function of time, both are continuous here in this particular case, right. You can see some more examples, like in a brand switching model for consumer behavior, that you are making a survey, the number of people whom you observe on a monthly basis who buy a certain brand of an item, say coffee or something, like this in a consumer behavior. When you want to do the market research, like you would do this. So, then the number of people is what on monthly basis, right. You can see now what is the situation. Number of people waiting at a bus stop at any time of the day. So, time is continuous that you are looking at it. Suppose the same thing, if you are looking at every hour, then the time becomes discrete, the number of people also become discrete. That is why the specification is important, at any time of the day or at every hour, like if you specify accordingly, then accordingly your state space and index space would take the difference. Size of population at a given time, right. Waiting time of the 10th person of a day who arrive at a bus stop. In a time sharing computer system or in a production system, the number of jobs waiting at any time, right, and the time a job has to spend in the system. The number of jobs would be discrete, time is continuous, the time a particular job has to spend in the system is continuous, right. So, you can look at that. So, the classical and the more useful classification of stochastic process is by the nature of dependency relationship among the random variables, because that is what is really make the study of stochastic process distinct and more useful than classifying based upon the nature of parameter space and index space. So, this once you make this kind of grouping or relationships, then that particular group can be studied in detail, and it helps in stochastic modeling, because then you have developed already so many tools for the application, and then the moment you see such a scenario existing in a real life system, then all these tools can be applied in a immediate manner, right. That is what is the idea. So, now we look at, based upon the nature of dependency of stochastic process, what are the different classes of stochastic process that we can have. Of course, there are plenty, like but we will see the major ones, the main important ones. Independent process. So, this is the most trivial stochastic process. where actually there is no dependency among the random variables. So, if you are looking for the FDDs, the joint distributions, then they are just product of their marginal distribution. So, if you know at each time point what is their marginal distribution, then you know completely about the process, right. So, this is example could be an IID noise or simply white noise process in some people call it in say areas like signal processing and other places where it has applications. Is basically the independent one, it is IID sequence essentially or IID family in this particular case. IID means we just want independence only, but if its distribution also is the same, then it becomes IID in a way. And the other group is what we call stationary processes. So, again the word stationary we are referring with respect to time, right. So, a stochastic process is said to be stationary or sometimes strictly stationary if their joint distribution functions, which we are written down as this FDDs, they are invariant to shifts in time. Meaning, if you have a delta, right, and if you are looking at the distribution of the joint distribution at the time t plus delta, where t is a vector here, x is a vector here, right. This capital X is the n vector, that suppose if this is the n element set, then of course this is the all n element sets. Delta is a single quantity. Now, if you shift the time by a delta, right, the distribution does not change. So, that means the whole thing. So, if you know one n dimensional modular distribution, joint distribution, then you practically pretty much you have known all n dimensional modular distributions of the process, right. It reduces to a great extent the requirement of testing whether the process is stationary or knowing the FDDs, the finite dimensional distributions, right. So, basically the process is in some sense probabilistic equilibrium and the particular times of the process being examined are of no relevance, right, like any other time in some sense, right, because whatever the distribution that I am going to have at time t, now 5 units down the line or 4 units prior to that I would have had the same distributions, that is what this would mean, right. This is we call stationarity in strict sense because we require this to be in terms of distributions. A weaker sense, which is what is called a wide sense stationary or covariant stationary or weakly stationary, if it possesses finite second moments, right, and expectation of xt is expectation of xt plus delta, which means the mean is equal across even if the time is different, but the covariance which is defined to be this depends only on the delta. Delta means the length of the interval in which you are looking at the two random variables from the same stochastic process, xt and xt plus delta. So, it depends only on the delta, right. If it is a function of delta alone, then you call this as wide sense stationary or covariant stationary. You are requiring not in the distributional form, but only based upon the first two moments, joint moments as well, right. Obviously, a strictly stationary process would be wide sense, but need not be the other way, and it finds application in time series, signal processing and so on, right, in different places. Then comes a process which is also relevant for our studies, which is I would highlight like which are the processes which are more relevant to our studies while making these classifications. Okay. So, a stochastic process is said to be a process with independent increments if the increments of the process are independent. What are the increments means? So, you are looking at this xt, you are picking up the time points t0, t1, t2, t3 and so on up to tn. You are looking at these time points, okay, and for all n, arbitrary some n plus 1 time points of this nature. Now, you look at the process how it has moved from t0 to t1 and t1 to t2 and t3 to t4 and so on, right. So, that difference, the difference in the state of the process, right, how this is what is that representing that random variable, that this is what is called as an increment of the process in a time in an interval t0 to t1. So, this is what you call the increment. I mean, it need not be increment, does not mean always goes up, but it is just the change that you make. So, we call it as increments of the process, right. So, this is the increments, this is the, so these increments, if they are all independent, right. So, that means what has happened in the previous interval, right, and what is going to happen in the next interval, right, starting in a two distinct interval, they are independent, that is what it would mean, right. So, this is what we call process with independent increments. Now, if the increments depends only on the length of the interval, but not on where this interval is placed, right. So, that means the increment x t1 plus h minus x t1 depends only on h and not on t1, right. Then you say this is a process with stationary increments. Okay. Now, you could have a process with both independent increments as well as stationary increments. For example, the one that we are going to be used very quite frequently or extensively in our queuing analysis is Poisson process, which is a process with both independent increments and stationary increments. And another process which is also will be used in the advanced level of queuing systems in the analysis is Brownian motion, which is also of this nature, right. So, this is a particular class. Then you have another class which is called martingales, okay, right. So, this a stochastic process is called martingale if it finite moment exists for all t and this conditional expectation equals a n. What is this? What is this conditional expectation? If you try to understand that, if you try to look at this is the history. This is the history of the process that is given to you in some sense, right. So, you look at time t naught the process started in the state a naught and at time t1 it was in state a1 and so on, and at time tn it was in state an. Okay. Now, what is the expected state in which it is going to be at time tn plus 1 given this history, right. If it turns out that this conditional expectation is equal to an, right, then for all t naught t1 and do this for all values of a naught and an, if this satisfies this, then the process is said to be a martingale. Okay. So, basically the states I mean what it means is that the expected value of x t plus 1 given the past and present values of this equals the present value of x t n. So, for example, in a game situation this could be represent a gain and if what is going to be the gain in the next time point after playing one more game and the current. So, the expected value you could actually end up with either higher or lower, but the expected value of that if it is same as what I have currently, right. So, that in some sense you would call this as fair game, right. It is a fairness. So, this is the equality represents in some sense the fairness of that. Okay. So, this is what a martingale means. Suppose if it is greater than and less than, then you have a different nomenclature, sub martingales, super martingales and so on, which anyway you will know. So, this again finds applications in queuing theory as well in a very advanced level along with Brownian motion and martingales, but we will not be using that here. Okay. And also, but this is a very important concept in financial mathematics, actuaries, insurance like whatever you do, martingale theory plays a critical role, because you want to for example, in financial maths or in insurance for example, you want to arrive at a premium which is fair in some sense. How do you define the fairness, or how do you quantify, or how do you model that fairness? It's through this martingale properties, right. So, that is how it comes there. Financial maths again, pricing of derivatives for example, like how you will price, what is the price that you are going to give. So, it is the fairness idea, that is martingale plays a role. But the most important stochastic process that we are going to use extensively, at least in the more than almost throughout the course in a way, if we have to say, is what is called as Markov process in general. Okay, so what is a Markov process? It's a stochastic process that satisfies the Markov property. So what is Markov property? Markov property is what is in general is given here, right. So what is this? What does this mean? Again you look at here, this is, see, martingale we represent in terms of conditional expectation, right, and here it is in terms of conditional probabilities. So if you know the process started at x naught at time t naught and the process moved to x1 at time t1 and so on xn at tn, and given this history, if I want what is the going to be the probability of x at tn plus 1 would be less than or equal to x. If this conditional probability is equals this conditional probability, meaning that the same event but with the information that is only that the last known position, that is x tn is equal to xn, which means all these prior things does not give any does not make any impact in this computation of this conditional probability, right. So if this is what is the Markov property. So basically what you are trying to do is that you are trying to connect this the random variables in this stochastic process through a one point dependency or one time point dependency, which means x t n plus 1 is in some sense connected to x t n only, not an x t n minus 1. What was the process value or what was the state of the process at time t n minus 1, t n minus 2 and where it started has no bearing on these computations, right. Of course, this definition would true and this you can do only if this conditional probabilities are well defined. We are assuming that they are well defined. Okay. So, the left hand side if it is defined, the right hand side is automatically defined. So, that is we are assuming, and if that is the case, then you have, if this is true for all time points and for all n and for all values of x naught and x, then only the Markov property is true, right. It is not that for a particular values any. Of course, that this is true with respect to any general definition that one gives, like in same thing it is here. So, this is a very simple but highly useful form of dependency which was given by Markov, and hence this Markov process. It is 1907. So, it is 115 years or more than that. Before that these things was defined and used. So, it is a highly useful form of dependency because you would find like you are extending the dependency only to the last known state of the process. Okay. Now, basically like in informal way, if you have to say the future depends on the present and not on the past, but in queuing, for example, if you are looking at the number in the system, what was 10 hours before, what was the queue size, does it matter. Whether the queue is going to build up, I mean in the 1 hour from now depends only on the current state. So, that is where naturally the applications of this come. Okay. Again, as we said, the process with a discrete state space will be referred to simply as Markov chain. So, that is a word that we will use. The Markov process we will not use, Markov chain. Whenever we say Markov chain, we always mean that the underlying state space is discrete. Okay. So, this is a discrete time Markov chain, which means discrete time, discrete state Markov process, which is we will simply call it as a discrete time Markov chain, or in short DTMC, is the easiest to conceptualize and understand, and in fact we will start with this DTMC only little later. Okay. So, the duration in this case one can understand the duration of the time the process stays in a state is distributed as geometric distribution in case of discrete time and exponential in case of continuous time. That's a main property, the major property of our holding time or sojourn time in a particular state of the process is exponential or geometric depending upon, and like these are the only distribution which has this memoryless property. So, that is where this thing comes. So, Markov process are central to the study of queuing systems. So, again it has wide applications in a wide spectrum of areas including queuing theory, statistics, economics, finance, population dynamics, physics, information theory, artificial intelligence, etc., etc. Now, birth-death process is a very important special class of Markov chains or Markov processes, where the transition takes place only to the nearest neighbors. That is you will have a state space in an ordered manner, and the transitions from, the process moves from one time in the next time whenever it makes a move, like it moves only to the nearest neighbor states. Okay. So, that is a restriction that we are imposing on that movement, and then you get what we call birth death process. Our first queuing models that we are going to start will be based upon this birth death processes. The whole maybe about 2 weeks or something that we are going to see in the model, different models, they will be based upon this birth death process. Again, as I say, we are defining a different classes, say Markov process, okay, again a subclass of Markov process, the birth death process. The reason is that the more finer it becomes, that you can get the more information, more theory that you can develop with respect to that particular class as well, at least that is the idea. Now, if you extend this in a way, what you would get is what you call semi-Markov processes. Okay. So, this is a generalization of Markov process wherein we permit an arbitrary distribution for the duration of the time the process stays in a particular state. Rather, in Markov you saw it is either geometric or exponential depending upon the time is discrete or continuous. But if you allow allow the time a process stays in a particular state need not be exponential, it could be any other non-negative distribution. Suppose if continuous, if you assume, then what you would actually get is a semi-Markov process. Okay. But at the time of transitions, it behaves like an ordinary Markov chain. Okay. At those instances, we say that we have an embedded Markov chain, and this is the idea that we will be using it when you are looking at non-Markovian or semi-Markovian queuing models. They will be based upon this semi-Markov processes. We will see more when we reach there. Random walk is again another important stochastic process, which is defined as Sn is a discrete time if you are looking at it. Then of course, the Sn is defined as x1 plus 2 xn, where S0 is 0 and xi's are IIDs. Okay. If the index is from continuous, then you have a continuous time random walk, which is for example a Brownian motion. So, here the emphasis is on the position of the process after n transitions. That is what random walk would mean. So, a popular random walk is a simple random walk wherein the process makes a transition only to the neighboring state, and symmetric random walk if the probability of making to the neighboring states, if they all have equal probabilities. So, that is what you call symmetric random walk and so on. So, one can have many different properties derived for such specific cases. As opposed to random walk case, in a renewal process, it is also almost some like it will look like if you look at this description S0, Sn and n, these are all IID non-negative random variables, xi, everything if you look at it, it looks like the same quantity. But here in a renewal process, the interest is counting the transitions that take place as a function of time. So, number of events that has happened, not the position of the process at that point of time. We are looking at the number of events that has happened by time t. So, that is what you define this nt to be the maximum of n such that Sn less than or equal to t, and this process nt is what then you call it as a renewal process. Okay. So, that is the difference between the interpretation of in a random walk and in a renewal process that you are seeing it here. Then again a Gaussian process, where which means that the finite dimensional distribution, if they are all multivariate normal distributions, then you get the process, you call the process a Gaussian process. For example, this is very useful in statistical modeling and various ideas, and then machine learning and so on. Okay. Then you have the Brownian motion, which is also called as Wiener process. So, if it satisfies these properties, right. So, here it is basically it starts at 0 and it has independent increments. Okay. And it has Gaussian increments, meaning it has a stationary increments, and the increments are following a normal distribution or a Gaussian distribution with mean 0 and variance u. So, again you see that this difference, the increment depends only on its difference u. So, this also has stationary increment, independent increment. The stationary increments also have the distribution as normal distribution, and also you have this paths are continuous. This is also another defining property of Brownian motion, which we have not put up in any other distribution that we have seen, because we never talked about this path properties, but here we are assuming that the paths are also continuous for this. Okay. Again, this is a major application in different places, like in one of the main areas are finance, and it originated from physics because by Einstein and others, right. statistics, etc. So, like this, there are many different classes of stochastic process one can define, and depending upon for example, Levy process and so on, and one can define it depending upon certain properties, that if it satisfies certain properties, you call that particular group by some name and then start developing the properties, so that it can be used readily. So, that is the purpose of developing the theory part of any field, and in stochastic process as well that holds true. And once you have the tools and everything available, so you can simply use it in when you are trying to apply that particular process to model certain real phenomena. Okay. So, this is the overview, right. The most important processes are Markov process, birth death process as a special case, and its properties, discrete time and continuous time is what we will see for the next 2 weeks. And once we understand this, then how we will apply or make use of the results, or we will apply these results to the modeling, and once you model and then the analysis of queuing systems, like you will use these tools, right. Later on when we require, like we will introduce the renewal process and semi-Markov process to analyze more generic queuing models, semi-Markovian queuing models rather we will say, right. So, that we will do it, will come later, but the next 2 weeks will be based upon Markov chains, discrete time as well as in the continuous time. So, that is what we will be seeing next. Okay. We will see you then. Thank you. Bye.